Welcome to our short practical stats video, What to Do with Outliers. Outliers are a fact of life. How do you deal with them? We're going to look at two main points. First, what not to do with outliers. You should not delete outliers without evidence from outside of the data set itself. And you should not use outlier tests to define bad data. Second, we're going to look at what you should do with outliers. Primarily deal with outliers based on their three main causes. And the cause for the outlier will help you to decide what to do with it. If you'd like more information on this topic, you can take our Applied Environmental Statistics course. It's at practicalstats.teachable.com, our training site. So the data set that we'll look at is nitrogen concentrations in precipitation, and there were two groups: precip in industrial areas, precip in residential areas. You see the box plots of the data here. Generally, the industrial data are higher than the residential data. We do see this one outlier, though, for the residential data, and that draws the mean up above over 75% of the data. It's up around the 80th or 90th perhaps percentile. So when we want to compare these two groups, it's really important to decide what is the characteristic that you're trying to say might differ between these two groups. If you're interested in the means, because of that outlier, with the mean being high, it's pretty close to the mean in the industrial group. So if you run a t-test on the means, you do not find a difference. If you run the rank sum test on the frequencies, the rank sum test is a test for whether one group generally has higher numbers than the other. It's going to look at all of the data in one group, compare it to all the other data in the other group, and count the proportion of increases and decreases. So if the null hypothesis for the rank sum test were true, about half the time the industrial group would be greater than the residential group, and about half the time the residential group would be greater than the industrial group. That's a non-parametric test, a test on frequencies, and you can see from the box plots that it's more often true that the industrial site is greater than the concentrations at the residential sites. And so we get back a p-value of 0.049. We would declare that the two are different, and that the industrial group generally gives you higher concentrations than the residential group. The outlier in the residential group just counts as one other observation. It is not unique in its influence on the result. It has the influence of 1 over n. For the t-test, observations, because you're dealing with a mean is what? It's a standardized total. This observation has a very strong effect on the total. It has more than 1 over n weight on the final result, the final total of the concentrations in the residential group. So outliers are things that have worried people, particularly applied scientists, for some time because they seem to cause problems with parametric tests like the t-test. What is an outlier? Outliers are observations that are different in value than the rest. There is no attribution of good or bad to an outlier in statistics. Outliers are not automatically considered bad data in statistics. In fact, they may be the most important observations in the data set. Some people define outliers using an outlier test, and when they find them to be an outlier, they delete them. I'm going to tell you that that's a really bad idea. If you want a reference for that, you can go to the new version of Statistical Methods in Water Resources. That's the second edition. Came out this year, 2020, by myself, Bob Hirsch, and 3 other authors. It's in the series U.S. Geological Survey's Techniques and Methods. It's Book 4, Chapter A3. You can download it at this URL. It is free. So, in Chapter 3, I believe it is, we state that this is a dangerous and unwarranted practice to define an outlier just based on the values in the data set itself without any outside evidence of being wrong, and then deleting that outlier. Outliers are often the most valuable observations. They can tell you that different conditions were operating. For example, there could have been a very, very large flood during the period of record, one which occurred only once in 30 or 40 years. So some unique climatic conditions. It could be the most important observation in the whole 30-year period in order to estimate the mass of sediment or lead or other things that has been moving down the river system during that time. If it's a point with a value that you don't expect, it could be that you just don't understand the system as well as you think. There may be different processes operating under certain conditions. The outliers can give you a clue to where those conditions might be. A somewhat silly illustration: if you're collecting samples of rock and you're measuring gold content and you find one or two samples where the content is really high, you've hit a vein, are you going to throw those data away because they're not like the others? I don't think so. Outlier tests, let's talk about those a minute. With these outlier tests, an observation is determined to be an outlier if the data don't follow a particular model. And that model almost always is a normal distribution. So if an observation is declared to be an outlier, it's declared to be an observation that's unlikely to have originated from a normal distribution. That's all those outlier tests test for. And so if you find an outlier, it critiques the assumption that that data point comes from a normal distribution. And the big issue with outlier tests is that people often use these tests as a test for bad data. There is no statistical test for bad data. So there's a number of examples in the literature about people throwing away outliers. Here's one of my favorites from the Denver Post climate study, and it talked about a city in Alaska that it was warming very quickly over a series of years, and there were automatic algorithms programmed in based on probably the historical data, maybe on nearby sites in Alaska, and they used the mean and the standard deviation, and likely used something like the mean plus or minus 2 standard deviations, and anything outside of that was called an outlier, and the computer just threw those out. And so most of the data during that warmer year was thrown away. Or a government report where they deleted observations that were designated outliers by a particular test. This is one of the standard outlier tests. This was official guidance. That's a terrible procedure. So there's no test for bad data in statistics. Outliers simply tell you that data did not come from a normal distribution. Concentrations in water, air, soils, chemical data in biota rarely come from a normal distribution. You should expect outliers to occur in your data in natural resources. If that outlier is negatively affecting your test, like a t-test, that means you're probably using the wrong statistic, the wrong test. You really don't want to test on means. Just as an example of the problems with outlier tests, here are data that I generated. I generated them from one log normal distribution. So they are not from a normal distribution. They're actually less skewed than most of the data that I work with. The box here looks fairly symmetric. Symmetric meaning that the top portion of the box is about similar size to the bottom portion of the box. But it does have this one outlier, which is not unusual when data come from a skewed distribution like a log normal. But then an outlier test, Dixon's test, was run, and it picked out this point as being an outlier. Does that mean that it's bad? The answer to that is no. It's just not a point that came from a normal distribution. So I could take the logs of these data and then run Dixon's test, and it tells me that there are no outliers. Can an observation go from bad to good just with a log transformation? No, it's because it was never bad to begin with. It was simply not from a normal distribution. You should know that outlier deletion has been a somewhat frequent topic of scrutiny in court cases recently. Lawyers on one side are checking to see if people have thrown away outliers on the other side. And if they do, the reasons behind that throwing away are questioned. And lawyers know at this point that you really cannot arbitrarily delete them. You're going to have to explain in court why you deleted them. Was it just personal bias? You could just throw them out so that you got what you wanted to see. Do statisticians back that approach up? Yes, they do. So Barry Nussbaum, who was formerly the chief statistician of the US EPA, said, there are a lot of statistical methods looking at whether an outlier should be deleted. I don't endorse any of them. Ed Gilroy, who's formerly a statistician at the U.S. Geological Survey, gave one of my most favorite quotes of all time. Treat outliers like children, correct them when necessary, but never throw them out. And finally, Marcia McNutt, who was the editor-in-chief of Science, was doing an editorial on the types of errors that people have in their papers when they submit an article to Science. The editorial was called Raising the Bar back in 2014. And she cited a paper that did things the correct way. Her quote was that clearly, for this data, throwing out a few of the data points by declaring them outliers would have improved the fit dramatically to some model. Maybe it was a regression model. It was not too long before it was realized that those outliers were the key to a more complete understanding of the long-term rheological behavior of the oceanic plates. So the fact that they did not follow the temptation to throw away those outliers led them to a greater understanding of plate tectonics in some way. If that's so, what should you do with outliers? There's three possible causes of outliers. First, an error in measurement. If you determine that there was an error, fix it if you can, or if you cannot fix it, drop the measurement. Outliers affect the mean, and that's the reason that they have been thrown away in the past. So here's an example. This was the residential nitrogen data that we looked at earlier, and that outlier that was circled was at 9.7. What if it actually had been at 1.7? It's still the highest value. If it was at 9.7, the mean was 1.6. If you drop it down to 1.7, the mean is half of that at 0.84. So it strongly affects the mean. The mean is not a resistant, that's a technical term in statistics, not a resistant measure of the center. It's the center of mass. And when you have this big of a change in the data value, you're changing the mass, the total amount. However, the median, which is the center of frequency, doesn't change at all. The median is a resistant measure. So using statistics like the median, using tests based on percentiles, non-parametric tests, are ways of not throwing away the outlier, but not giving them a tremendous amount of influence on the outcome. So if you're really not interested in a mean, don't use a test on the mean. If it's a question of whether one group has higher values than the other, that's not a question that the mean answers. So choosing whether you should use the mean or the median, and the tests that go along with that, t-tests and ANOVA for the mean, tests on percentiles for the median, non-parametric tests, is one of the fundamental questions you have to address before you start looking at your data. And if outliers are present and you're doing a test on the mean, those outliers are a very good thing. You have found the high value events. You have measured those. If you're interested instead for typical values, you want to know whether how often something occurs. How often does one group have higher numbers than the other group for example, then you want to use a test on the percentiles, which would answer the question, does one group have higher numbers than the other, explicitly. And outliers won't strongly affect that result. The second cause of outliers is contamination from another population. So you were trying to mix two different conditions. And if the outlier represents the conditions you do not wish to describe, you can take all of the data, not just the ones that you would label outliers, but all of the data for that other condition and separate it out and describe those two conditions separately. So for example, here's a rectangle that has a sample measured at each of these dots. They're evenly spread across the study area. I believe there are 24 samples here. And the blue condition over here is different than the brown condition. There are much higher concentrations in the blue area. So if you wanted to know what the typical concentration was in this whole area, you could take the median. And the median would likely fall in this brown area, since these three values are going to be at the upper end. And the three, quote, outliers would not affect the value for that median very much. If you only wanted to describe the brown area, separate out the blue area, do not consider it, report back statistics for the brown area, and then possibly, if you're interested in it, report back the statistics for the blue area as well. What if you wanted to summarize the conditions under the entire rectangle? Well, then you do not want to separate them. You would want to measure the median or the mean, whichever is of interest to you, of the entire area. And the fact that these three were higher is a good thing, because we've sampled this area. We haven't just ignored it. In neither case would you just throw away these values because they were high. But we might separate them out if we're interested in characterizing this possibly contaminated area separately. Finally, outliers can be caused by the simple fact that most of the data that we measure come from skewed distributions. In that case, just keep the outlier and use a non-parametric test on percentiles, or if you are interested in the mean, and these outliers are then valuable, use something called a permutation test. You can find out information on this site or on our training site about permutation tests. And they are tests for means, but they do not require you to assume a normal distribution. They're a main topic in our Applied Environmental Statistics course. So in the past, the primary reason that people have used outlier tests to define an outlier is to throw away data prior to running a parametric test. That's a terrible method. You're going to miss the most important observations in terms of the mass. If you're not interested in the mass, use a non-parametric test or a permutation test. If you are interested in the mass, you do not want to throw away those outliers. Don't remove data in order to use approximate tests. That's the older t-tests and ANOVA that were developed in the 1930s and 1940s. Instead, use much more modern procedures. Remember our top 12 tip number 2 from the Applied Environmental Statistics course. Treat outliers like children. Correct them when needed, but never throw them out. In summary, outlier tests cannot tell you whether data are wrong, only that they're not likely to have come from a normal distribution. Do not use them to throw away data. Do not use them to define bad, quote-unquote, data. Field data in water, air, soils, rocks, biota are usually skewed distributions. They do not follow a normal distribution. Outliers are to be expected. So do not just delete outliers. Just remember, Albert Einstein was an outlier. Thank you very much for listening.